Chapter 36 is on population dynamics. Okay, so when we look at population dynamics, we're going to look at how quickly animals can reproduce and spread as one thing that we can look at. And there's a nice example of a European starling, and it's called Shakespeare's starling because people in New York brought it to the Americas because it was in Shakespeare's play. They thought it'd be just plain cool to have everything that Shakespeare ever talked about in New York. And so they brought over 100 of these things, and now there are millions and millions and millions of them across the United States and up into Canada. And they're actually a pest. They're a problem. They didn't know that when they brought it in, but they have become quite a problem. We've tried to eradicate them in California numerous times. It has not worked. They just keep coming back. Okay, so here's your starling population. Like I said, they were brought in 1890 or so by some Shakespearean society, something like that, in New York. And you can see that they rapidly spread across the entire country, all the way up into Canada. You could get rid of them in California, but they'd probably just come back from the rest of the country. So it's become a problem. Okay, when we look at population ecology, it is concerned with changes in population size and factors that regulate populations over time. So when you think about this, you need to be thinking about birth rate, death rate, how much resources are available to the population, what kind of predation's going on that will limit the population size. So there's different factors that will increase a population, high birth rate, lots of food, and there's factors that will limit a population, being preyed upon, or limited resources, high death rate, that will limit a population. Okay, population ecology is the study of how and why populations change. And a population is a group of individuals of a single species that occupy the same general area. Okay. Density and dispersion patterns are important population variables. So how dense the population is overall, and whether they're clumped up into little groups, or are they evenly spread out, or is it random? Those are population density things that we worry about. Right, so here you have an even dispersion of penguins. You have clumps of fish, and you can have random populations where it's random, right? So clumps are not necessarily random. It's the way things either move or grow. And then again, you have uniform. Okay. Life tables track mortality and survivorship in populations. Life tables and survivorship curves. All right, you're going to predict an individual's statistical chance of dying or surviving during each individual of their interval of the individual's lifetime. So let's look at this chart, and you can see here that between the ages of 0 to 10, you actually have, it's not a high mortality rate, but it's higher than from 10 to 20. And the reason is that you have infant mortality. When babies are born, they have a higher chance of dying. Once you've matured to the age of 10, your rate goes down because you're not going to die in birth here, and there's probably, this is mostly going to be things like accidents. Again, accidents here. And then as you get older, you'll see the chances of dying obviously increase till you get to 100% death rate, because no one survives this last age interval. Okay. There are 3 types of survivorship curves. So there's a curve 1 is a human curve where we tend to live a long time, kind of grow old, and then die off, right? So you get a little bit of infant mortality maybe, but generally speaking, most people live, we take care of our children. We don't produce a lot of children, so we take care of them until they're old, and then they die. Then you have the squirrel, and this is sort of the anomaly here. There's not a whole lot of this type 2 curve going on, but what this would represent is just a constant chance of death. You're just as likely to die as a squirrel when you're, 6 weeks old as you are to die as a squirrel when you're really old. It doesn't really matter for squirrels. They're equally likely to die along that line. And then you have this type 3 curve. And these are going to be animals that just produce a ton of offspring, just hoping that a few survive. So they just kind of thousands of offspring thrown into the sea or wherever. And many of them are going to die. You're going to get a huge drop off. But then once they grow to a certain size, they become hard to prey upon, and they'll live a long time at that point. Okay, so we use idealized models to help us understand population growth. So we'll take some mathematical models, and they can be quite useful to us. And when we look at exponential growth, it is the accelerating increase that occurs when growth is unlimited. It's exponential, so it's going to be a rapid curve up. All right, so this is the classic exponential growth. It's called the J curve. You have G is the population growth rate, which is how fast it's growing. That's the number we're looking for. R is the inherent capacity to reproduce. So how quickly is it reproducing? And N is the population size. So if you start with a really small N, if you only start with 2 people, you're going to be down here, and it's going to take a while to get going. But as the population increases, that curve gets steeper and steeper and steeper and steeper. Mathematically, you can think of this. Here are your exponents here, 0, 1, 2, 3, 4, 5, 6, 7, 8, down, okay? So, and this, by the way, is not for humans. This is a bacteria chart. But the idea remains that if you have one cell, it's going to divide. These are going to divide every 20 minutes. That's exponentially. You're going to say 2 to the 0 because that's 1. Then you're going to have 2 dividing. When those 2 divide, that's 2 to the 2. When those now become 4, they divide, and so on and so forth. That is the exponential growth. Each time they divide, you have a bigger jump because there's more of them. So that's why we call it exponential, and that's why it's going to go up and up and up very rapidly. Okay. Then there are limiting factors that can space, resources, predation again. There's things that are going to limit the ability of a population to grow. You usually cannot grow indefinitely. Okay. So when we talk about these, we're going to have this logistic growth. And if you look at, okay, so first of all, the model that represents the slowing of a population growth as a result of some kind of limiting factor levels off at the carrying capacity, which is the number of individuals the environment can support. So if you look at our original formula, don't get confused by these. These are really pretty easy. We have our original formula. This is the growth rate, this is the reproductive rate, and this is the N is the population size. And in this model, it's just going to go up forever. Well, very often there's some kind of carrying capacity, K, something that's going to limit it. And this K is going to limit growth rate. When we put that into this mathematical model, watch what happens. Let's say our population's very, very small. N is, 2 people or 3 people. It's negligible. Essentially what you have then is K over K, which is 1, and we have our original formula, G equals Rn, right? No change. When N is very, very small, we essentially have this kind of growth over here. When N reaches the carrying capacity, when it reaches K, you're going to get K minus K, which is 0, and then anything multiplied by 0 is 0, basic math, simple algebra, and it's going to level off. So at the point it reaches K, it's going to level off. And then everywhere in between, what it does is it just kind of slows the growth because you're going to be multiplying by a fraction over here. All right, so the equation G equals Rn and then K minus N over K, the one we just saw on the previous slide, describes a logistic growth curve where K is the carrying capacity. K minus N over K accounts for the leveling off of the curve. And again, that's because you're going to be multiplying by a fraction. All right, so multiple factors limit population growth. As a population's density increases, you're going to have more pressures put upon it. You might have limited food supply. When you get more density, there's an increase in disease. It's much easier for diseases to go through crowded city populations than when out in the rural areas. You might have predation increase and death rate. So you can have a bunch of things that are going to start to limit population growth. Okay. Abiotic factors such as weather can limit natural populations. So you can have exponential growth and then some catastrophic thing and you get sudden decline. Okay. Most populations are regulated by a mixture of factors, and you get fluctuations commonly, whether it's, because one year you have a bumper crop of seed, and then the birds increase, but they eat all the seeds, and then they level out, and the weather's great. I mean, you're just going to get a variety of things that are going to control population size. Okay, some populations have boom and bust cycles, and some undergo boom and bust cycles of growth and decline. And I like this little graph because you have a very simple graph showing the population of the snowshoe hare and then the population of the lynx. And you can see pretty regularly that you get a snowshoe hare increase, and immediately after, the lynxes start to increase because now they have a greater food supply. And then they eat all the snowshoe hares, and then they're all hungry. And the snowshoe hares come back, and then the lynxes come back. And then they eat them all. And this peak tends to be right on top of each other. But usually you'll get more like this peak here, where you get first an increase in the snowshoe hare, followed immediately by an increase in the lynx. And then they eat them all again, and it just keeps going like that, on and on and on. And that is a common cycle for many of the prey predator animals. Okay. Evolution shapes life's histories. An organism's life history is a series of events from birth through reproduction to death. Mostly what we're going to be looking at when we talk about organisms' life history is when they are reproductively active, how early are they reproductively active, and how many offspring do they produce. Okay, populations with so-called R-selection life history traits reproduce many offspring and grow rapidly in unpredictable environments. And a good example is actually not that century plant, although it's okay. It's better to look at things like weeds. Weeds will just produce tons of seeds and offspring just with the slight chance that something is going to survive. This R selection, the whole idea is that you're just going to produce tons and tons of offspring. Turtles do this. They'll just produce tons of baby turtles, and they'll get preyed upon when they're babies, but you're just hoping a few make it to adulthood. Humans don't do this, but we kind of used to do it more. A couple hundred years ago, people were having more children because they knew that a certain number were going to die before, medicine, and we had antibiotics and all that stuff that reduces our death rate. People had more kids hoping that 2 or 3 would live. Okay, then you have K-selected traits, and this is more what humans do now. You raise a few offspring and maintain relatively stable populations. So you're going to put a lot of energy into a few offspring. Other animals that do this would be like elephants. Sharks actually do this. There's a whole bunch of animals that will just have limited number of offspring, but they'll really protect them and care for them. Okay, so when we look at life history, traits are shaped by natural selection. So we're looking at a guppy here. There's actually similar guppies in 2 different ponds, and one pond has a predator that kills the prey mainly of small immature guppies. Well, what those small immature guppies were doing in that pond was being reproductively active very, very early on to account for that, versus another pond, I think in the Caribbean somewhere, where there were predators that were preying upon more mature guppies. Okay, principles of population ecology have practical applications. So when we look at population ecology, we're looking at conservation. And we want to manage our resources, right? You don't want to fish a population to the point of extinction because it does us no good. We run out of fish. So we have to look at the population ecology. And like I was saying before, some are R-selected and some are K-selected. Well, some fish produce tons and tons of offspring. But then there are things like sharks or dolphins and whales that will produce one or two offspring and take care of them. So if you fish those, you can wipe out the population a lot faster than if you fish things that are selected that will produce more offspring. Also, the ones that produce more offspring can come back if you haven't totally killed them off. They can come back easier again than the ones that are the K-selected. Okay, human population growth has started to slow after centuries of exponential increase. So, so we've been growing exponentially, and if you remember, the basic formula, the G equals RN. N is the base population, how many people are on the planet now. And the bigger N is, the more G becomes. And so as N gets bigger, as that base population gets bigger, you can see on the curve here, we're up here. For years there weren't that many people. You have a small dip where there's the plague, and World War I was also with that. And then you just have this exponential growth. It has started to level off, especially in developed countries. Okay, so this shows the ecological footprint of different countries, and it represents the amount of land per person needed to support a nation's resource needs. So if you look at the red line, basically everything above the red line does not have enough land to support the people on it. Insofar as having, I think they say an average of something like 2 acres per person. Everyone below the red line has enough land for what they have now. So if you look at New Zealand, they have land and a low population. So they're a good ways off that line. Australia has land, low population. Canada obviously has land, low population. You look at some place like Japan, which is very kind of closely packed together. They don't have a lot of land. It's a high density population. They are way off this line in this direction. The world on average is just off the line towards the deficit side. So again, it depends on how much land you have, and it depends on the total population where you fall. You'll see that we fall a wee bit off the line as well. Places like the Netherlands, even though they don't have a lot of people, they also don't have a lot of land, so they end up on this side of the line. Okay, the ecological capacity of the world may already be smaller than the population's ecological footprint. That's to say, if we wanted to have the population as it is now, the current size, without starving people in Africa, essentially, if you could get everyone to have, a reasonable life style, could the planet sustain that? Okay, so when we look at birth and death rates, we're going to look at the birth and death rates. Usually what happens is death rates go down and then birth rates follow. And sometimes there's a little bit of a lag. And when you have a little bit of a lag, you have an increase in population size. The chart you're looking at here is for Mexico, and you can see what happened here. So first of all, you have a blip. What's this blip? That is the 1918 flu again. There's the flu, not the plague. This is the flu. And World War I think, but mostly the flu. So let's ignore that for a minute. Here you have your birth rates, and they stay high even though people stop dying. Well, what's this difference? That's the increase in population you're going to have. So they stayed high for quite some time. People, kind of leveled off on how quickly they were dying, the death rates. And eventually what happens is these two tend to catch up. When women start saying, okay, I don't have to have 15 kids for 2 of them to survive, the birth rates tend to decline and start to match the death rates. And that's what's happened here. So now, actually, we are still like here. The population is still growing. That's the difference. That's the population growth. But it's leveling off. All right, so when we look at the age structure of a population, you have a couple of different possibilities. This is going to be the proportion of individuals in different age groups. And it can tell you what's going to happen in the future. Are you going to have a baby boomers all retiring like we do in the U.S.? So you can see the population kind of go through over time. If you look at a place like Afghanistan, They have a lot of kids, and so here's the ages 0 to 4. And you can see this is the number, how that shrinks. That's the number that die by the time they hit 5 to 9, right? That's smaller. They do not have a really good life expectancy. You can see basically their population dies off kind of quickly in Afghanistan. This is the reproductive age, so these are the people you're concerned with having more children. These are people, older than that. They're not having more children. And so you can see they have more of the R selection, right? They're going to have a lot of offspring, but they die off quickly. Then you have the United States. We have slow growth, pretty stable actually. Here you have the number of children. So it's actually decreased this year. Our population reproductively, we're having fewer children. Here's the baby boomers up here. So this chart's a little old because they're actually a little older by now. But you get the little bubble where the baby boomers are, and that will go through, and that's why nursing is a good thing to go into, because a lot of them are going to retire soon. Then you have a place like Italy, and they actually are not replacing their population. So their population is decreasing in size. They don't have enough children to replace. Neither does Japan, and there's a few other countries that are decreasing in population size. So they're having fewer children. This bulge here were the kids when they were still having more kids, but they've slowed off. The reproductive rate in Italy has slowed down. Okay, so increasing the status of women may help reduce family size. They've done many, many studies showing that the more educated women are, the fewer children they have. It doesn't necessarily correlate to the education of the man. It correlates more to the education of the woman.